Hi there, yes, coming to this question, separation of variables, question 13 of 2019. I didn't fancy writing it all out, so I'm just going to run through the solution that we've found on the internet and try to explain it that way. So it's Laplace's equation. We've got some boundary conditions which we have to go through. We need to use separation of variables to get a form of an infinite series. So that tells us that we're going to be doing Fourier. That's the boundary that we're going to be integrating, which you'll see later. Okay, so here's the solution. So we're going to assume the solution is u is two functions x and y. So that means that when you differentiate them like the Laplace equation, you're going to get a second derivative of x times y and the second derivative of y times x, and then a bit of manipulation to have just the function of x, just the function of y equals this constant, which we're going to name minus lambda. So a bit more rearrangement. So you put just a differential equation in x with lambda, and we're given the boundary values in the question 0, 1, and 0. Now in the solution, just skipping a bit here, it says that this is a special case, blah blah blah. It doesn't really matter. You could figure out what it was anyway using the technique as normal, which is put the boundary values in and try and figure out what the constants are from the solution, and you would end up with that anyway because that's what it gives, and therefore the eigenvalues are that. But if you can do a bit of a shortcut by spotting in the handbook that this is a well-known special case problem, even better, whichever. It doesn't really matter. Okay, so that's what we do for that one. So we found that the x would be sine n pi x with those eigenvalues, and then if we know what lambda is, we can then put it into this, and we get a new problem then, which is second derivative of y minus lambda, which we just found, y equals 0. And for that one, the solution is this hyperbolic. We use hyperbolic really just because it's a bit more convenient. E to the x. The solution would be actually normally a combination of exponentials, but it's a lot easier just to describe it as these, as we'll see a bit later on for the actual solution. Again, we've only got one boundary condition, or one homogeneous boundary condition for this, i.e. equals 0, and that tells us that a n is 0 from that, because if you put 0 into it, you get cosh of 0 and sine of 0. Sine of 0 is 0 anyway, but cosh of 0 is 1. So if this is 1 and the answer is nothing, then this must be knocking that 1 out, so it must be 0. So we assume from that the answer is bn sine n pi x, or n pi y. This is a mistake, isn't it? It should be y's there. Watch out for that. Tut tut. So sine n pi y is what it should be. Okay, so that means that the actual solution is u of xy is xy, those two things which we just found, sine n pi x, which was the eigenfunction, and for y, bn sine n pi y. The b's now become bn because it's because of the n in the function itself. Now the next bit, it just suddenly becomes alright, stick a sum sign in front of it. Well, the reason we do that is because of the final the final boundary condition. Here it is, which we want to apply. Okay, and if we just put x1 minus x is equal to, forgetting this for a moment, that doesn't really get us very far. So the reason we put this idea of a sum of all the terms is basically to do the next part and figure out the actual solution, the particular solution. Because we know that if this is the solution, any linear combination of this is a solution as well. That's why we can put it. So that's what we do. So we've got this is that. Now, so basically we need to make this look like this and then try and figure out what Bn is, so that's the case. So we're just going to change this into a Fourier sine series, and that's going to have a sine n pi x in it, or something like that. And from that we'll be able to figure out what Bn is by comparing coefficients. So the next statement is, alright, let's write this as a sum of sines with some constant. First thing is we need to figure out what the constant is to know what the correct signs are to describe it. So for that, we're just going to refer to the usual technique of calculating a Fourier series, which is the function itself, x minus 1 times by sine n pi x. So we've now got a bit of integration to do. These are known integrals, you can look them up. There you go, standard integrals, page 23. You can look it up. This should probably be the case with the exam. They won't give you a particularly stupid integral. They'll give you one that is one that you can look up or easy to do. So churning through all that, which I won't go through, but it's just integration of those things. That's the answer to it. You put 1 and 0 in. There we go. And go through all that. And we end up eventually, essentially what we're nearly always going to get is some kind of function of cos, because if we're doing a sine series, we're going to get a function of cos in there. And cos n pi usually reduces to minus 1 to the n, i.e. when n is 0, it's 1, when n is 1, it's minus 1, and so on, because of the way that cos changes for pi, 2 pi, 3 pi, and so on. So we end up with this expression, so that's what Bn equals here and here. So the combination we need of signs is governed by this recurrence relation. But when n is even, this recurrence relation. So when n is even though, Bn will be 0, because when this is 0, 2, 4, whatever, this becomes 1, and 1 minus 1 is 0, and the whole thing gets taken out. If n is odd, then we're just left with, this becomes 2, and that becomes 8, and then it's 8 over n cubed, pi cubed, which is the same thing as 2, n pi, all cubed. Okay, so, haven't we got that? We now know that this is our answer. So, but why has it changed to n minus 1? Well, because we're only dealing with odd terms, so we want an odd sequence here. So instead of being n pi x, it's 2n minus 1 for the odd sequence, 1, 3, 5, 7, 9, and so on. So that's our answer we got originally, sine n pi x, sine n pi y, which it would be, but the boundary condition is being applied there as well, so that's where y equals 2, so that's where the 2 there, is equal to our sine function, sine n pi x as it was, Bn. So there's the Bn. So that's this one, that's this one. So if we put this, figure out what this is, now put it there, and equal to that. And we're also applying this boundary condition, so there's a 2 there. Hope that makes sense. It is complicated. So we should have this kind of sentence here, this line, that the solution is equal to this Fourier sine series of this condition when y is 2. And now what we can do is compare coefficients. So we've got sine 2n minus 1 pi x and sine 2n minus 1 pi x. Might implies that this is equal to this times Bn, which is what this says. So Bn sine 2n minus 1 pi is equal to this. So the solution to the problem then is Bn is equal to this divided by sine of all that, and then we put that in there. This is our solution. Oh, not even there. There. Our general solution. So on there, the n's are going to change to n minus 1, but we're going to have that on top, sine 2n minus 1 pi x, sine 2n minus 1 pi y, and then times that by Bn. Bn we just found out through all that working is this divided by this. So there is that divided by that is there, and then there's the sine 2n minus 1 pi x, sine 2n minus 1 pi y, and that's the final answer. Right, hope that makes sense. If you've got any questions on it, fire them away. I'll try to answer them. Alright, good luck.